In this lecture, I'd like to talk about energy stored in capacitors. So let's remember what we were doing last time, talking about capacitors and how they work. So here we have a circuit where we've hooked up basically a car battery to a large parallel plate capacitor, okay? And then we have a switch in there. All right, so if you consider this whole circuit to be a system, then and you consider that the capacitor is initially uncharged before the switch is closed, then what happens is when the switch is closed, you establish, because of the voltage in between the plates or in between the terminals of the battery, you establish an electric field in the wire. And then that electric field in the wire causes F equal to QE, right? A force on the electrons in the metal, in the wire, and electrons from the battery as well. And what that causes is the electrons to move from the negative terminal of the battery and build up on that negative plate. Okay, so it moves from the electrons move from the negative terminal to the negative plate that they're directly connected to. And then that negative charge repels the electrons in the plate on the opposite side of the capacitor, leaving a net positive charge there. And then those electrons move kind of counterclockwise down into the positive terminal of the battery. And this will continue until the voltage between the plates of the capacitor equals the voltage of the battery. So if it's a 12-volt battery, you'll have 12 volts in between the plates of the capacitor. Okay, so that's how that works. Now, when that happens, what's happening is charge is being moved around. And anytime you're talking about moving something, you're also talking about energy. So before the switch is closed, all the energy in this system is stored as chemical energy in the battery. And then when the switch closed, the energy was transformed from chemical into electric potential energy, and then, of course, some kinetic energy as the charge moved, okay? So the electric potential energy that ends up, well, if you look at the end result, so you start off with chemical potential energy in the battery, and then you end up with an electrostatic situation at the end where the capacitor is now fully charged and the voltage in between the capacitor plates equals the terminal voltage of the battery, right? So 12 volts and 12 volts, then nothing's moving anymore. And so you've converted chemical energy to electric potential energy at the end point. I hope that makes sense. And this electric potential energy is related to the separation of the positive and negative charges on the plates, right? And this is kind of similar to gravitational potential energy when you think about it. If you're holding your keys above the ground, right, there's a gravitational potential energy. Just like if you hold charges apart, you've got an electrical potential energy. It's kind of like that. So you can think of a capacitor as a device that stores not just charge, but also energy, right, in the form of electric potential energy between the capacitor plates. Now, the work done in charging the capacitor appears eventually, once the capacitor is fully charged, as the electric potential energy U, okay? Now, the electric potential energy in a capacitor with charge Q on the plates, on Q on either plate, plus Q on one plate, minus Q on the other, but magnitude Q, right? Stored on one plate, with a capacitance C and a voltage between the plates of delta V, you can write that electric potential energy as Q squared over 2C, which, using the equation Q is equal to CV, you can write in other ways as well. So Q squared over 2C is also equivalent to 1/2 QV, which is equivalent to 1/2 CV squared. And this applies to a capacitor of any geometry. All you need to know is what the capacitance of the capacitor is, and you can read that off the case, for example. Now, this energy stored increases as the charge increases and as the potential difference between the plates increases, or the voltage between the plates increases. Now, in practice, you can't just crank the voltage up to whatever you want it to, because you will have breakdown eventually, depending upon what the dielectric is. It might be a larger voltage that you can crank it to, but eventually you'll get sparking and breakdown of your capacitor and you'll burn it out, okay? The discharge will occur between the plates. The energy stored is actually stored in the electric field. We can think of the electric field as the mechanism for the energy storage. Now, in a parallel plate capacitor, the energy can be expressed in terms of the field as 1/2 times epsilon naught AdE squared, okay? And that comes from the equation for let me show you. Okay, that comes from 1/2 CV squared. We have an equation for the capacitance, which is epsilon naught A over D, right? And then we can plug in for the voltage in between the plates in terms of the electric field. So remember that delta V is equal to ED. And so if you plug in for that, then you end up, instead of 1/2 CV squared, you end up with 1/2 epsilon naught AdE squared, where E is the electric field in between the plates. Okay? Now, if you think of the volume of a parallel plate capacitor, right? Let me pull back the parallel plate capacitor picture real quick. Here's your, well, let me pick a bit better one. Let's go back to here, okay? So here's our parallel plate capacitor, right? And if you wanted to look at the volume in between the plates of that parallel plate capacitor, remember that the equation for the volume is the area of the base times the height of any rectangular solid. So if the area of this plate is A and the distance in between the plates is D, then the volume between the plates would be A times D, right? Okay, so what we can then do is show you that here you have 1/2 epsilon naught AdE squared. This A times D, that's just the volume in between the capacitor plates, all right? So if you wanted to divide out by that volume, then you'd have an energy per unit volume, which is known as an energy density, right? Energy per unit volume. And the volume is AD, okay? So if I wanted the energy density, which is often symbolized by lowercase u with a subscript E, excuse me, then that would be 1/2 epsilon naught times E squared. And so you can see that the energy is related to the field. So the field is what stores that energy. The more electric field that you have in between the capacitor plates, the more energy that's stored. And then of course that electric field comes from the charge, right? So the more charge, the more field. Now, we obtained this expression for energy density by using a parallel plate capacitor example, but it's actually valid for all electric fields. If there's an electric field existing in space, energy is being stored in it. All right, so let's do an example problem using these ideas that we just discussed about energy on charge and charge on capacitors. How strong are the voltage and the electric field between the plates of a 0.8 microfarad air gap capacitor if they're 2 millimeters apart and each has a charge of 72 microcoulombs? Part B, what is the energy stored in this capacitor? Part C, what is the energy density? And then part D, what's the new capacitance and voltage between the plates if instead of air, you put in a polystyrene sheet, right? And you stick that in between your plates. So this is the question. Okay, so let's do part A first. How strong are the voltage and the electric field between the plates of a 0.8 microfarad air gap capacitor, 2 millimeters apart, each with a charge of 72 microcoulombs? Okay, so first we're going to solve for the voltage and the electric field between the plates. We know that the equation for capacitance is Q is equal to CV. Okay, so if we rearrange that, V is equal to Q over C. So we can find the voltage in between the plates by taking the charge, which is 72 microcoulombs, and dividing it by the capacitance, which is 0.8 microfarads. And when we do that, plugging that into the calculator, we get 90 volts. Remember that micro is 10 to the minus 6. So you're taking 72 times 10 to the minus 6 and dividing by 0.8 times 10 to the minus 6, and then you get 90. Now, the voltage is equal to ED. So the voltage in between the plates of a parallel plate capacitor is going to be the electric field between the plates times D. So rearranging that, E is equal to V over D. So that's going to be 90 volts divided by the distance between the plates, which is 0.002 meters or 2 millimeters. And when you take 90 and divide by 0.002, you get 45,000 or 45 kilovolts per meter. Okay? Now, next is part B. What's the energy stored in the capacitor? Okay, well, we have the equation for the potential energy of a charged capacitor. That's U is equal to Q squared over 2C, which is equal to 1/2 QV, which is 1/2 CV squared. And then you just pick which one of those three equations is most convenient to you. The one that I thought was the easiest to look at was the 1/2 QV one. And since I know the voltage between the plates is 90 volts, now I'm good to go. I just multiply 1/2 times the capacitance, or times the charge Q, which is 72 microcoulombs, times the voltage in between the plates, which is 90 volts. Remembering again that 72 microcoulombs is 72 times 10 to the minus 6 times 90 times 0.5, I end up with 3.24 times 10 to the minus 3 joules, or 3.24 millijoules. Remember that the lowercase m is the SI prefix milli, which means 10 to the minus 3. Now, the energy density equation, U sub E, is 1/2 epsilon naught times the electric field squared. Remember that epsilon naught is 8.854 times 10 to the minus 12 in SI units. It's that fundamental constant of nature. It's given in the textbook and very Googleable, right? So we already solved for the electric field, which is 45 kilovolts per meter or 45,000 volts per meter. So now we can plug in 1/2 times epsilon naught times 45,000 squared gives me 0.009, or 9 millijoules per cubic meter, because an energy density is an energy per unit volume, so joules per meter cubed, right? Last, part D, what if you put a dielectric in there? What would happen then? Okay, well, the equation for a capacitor with a dielectric is C is equal to kappa times C naught, where kappa is the dielectric constant and C naught is the capacitance without the dielectric. So since we have the dielectric constant is 2.6, then we multiply that times our original capacitance, which is 0.8 microfarads, and 2.6 times 0.8 is 2.1. So the new capacitance of our dielectric, of our capacitor with the dielectric, is 2.1 microfarads. Now, what's the new voltage? Well, V is equal to Q over C. If the charge in the capacitor doesn't change, in other words, if you don't leave it hooked up to a battery, forcing the voltage between the plates to be the same, and instead you charge up the capacitor and then isolate it from a battery so the charge is just sitting there and can't go anywhere, and then you shove a dielectric in, what that will do is it will drop the voltage in between the plates. So V is equal to Q over C. 72 microcoulombs divided by our new capacitance of 2.1 microfarads gives us 34 volts. So the dielectric being shoved in between the plates of the capacitor without being connected to the battery forces the voltage to drop to 34 volts. All right. Okay, that's it. And that also concludes some of the chapter 17 material that we're going to cover here in online lectures. I hope all that made sense. I hope you understood it, and I'll see you around.